Okay, so again, my name is Pavel Raykov, and here actually I work with Benny Appelbaum at Tel Aviv University. Okay, so this is a joint work with Martin Hirt from ETH Zurich, and this kind of was the last piece of my PhD studies, and it was presented at Asia Crypt, at the last Asia Crypt. So the title is Efficient Multivariate Broadcast, so we're going to talk about efficient implementation of a broadcast, a distributed primitive. Okay. Oh, good. Okay, so let's start with a definition of a broadcast. We have a setting of n guys labeled P1 through Pn, there are n parties. And one specific party, P1, has some input he wants to consistently distribute to everyone else. So I think of broadcast as a megaphone, as a tool, as a device that takes input from one of the parties and distributes it to everyone else in a consistent way. Okay, so it takes V and sends it to everyone. So just before going into the details about the broadcast primitive and how to implement it, very briefly we can say that there are multiple applications of this primitive, and essentially like any distributed protocol that does something most likely is going to use something like a broadcast. So one of the recent applications is a Bitcoin. You want to broadcast your transaction to everyone. Okay, good, it's good for us. Voting, you want to vote, you want to broadcast your vote to everyone such that everyone see that you voted. Another application is secure storage. You want to broadcast pieces of your data such that they are replicated in a consistent way. And in general, any multi-party computation protocol, it's actually not any, but let's say 90% of them, they use broadcast. So it's an essential primitive which we like to optimize. Okay. So in this talk, we're going to talk about broadcast protocols and what are they. So we have our broadcast primitive. And this is what we're going to use. This is what we want to use. But unfortunately, in the real life, we don't have it. So in the real life, we have something like point-to-point channels. So a broadcast protocol is a way to simulate a broadcast channel using point-to-point channels. Okay? So you can think of it as a way to kind of hear the broadcast. It works as a megaphone. It's a way to globally communicate. And here, you can see it as a way to locally communicate via point-to-point channels. So broadcast protocol is a way kind of to use local communication to simulate global one. Okay. So, and before going further, so far, this task seemed like an easy task. So if you want to simulate broadcast, you can just let P1, the sender, to send the value he wants to distribute to everyone else over the point-to-point channels. So, okay, so I am P1, the sender, I can send the value just over the point-to-point channels, and everyone will agree on the value sent by the sender. It's very easy. So what makes this talk hard, kind of, and our goal hard, is that we assume that some of the parties may misbehave. So this is so-called active corruption. So some of the parties can be Byzantine and can behave maliciously. So in this case, the sender, for example, can send different values to these guys, and the consistency property of a broadcast can be violated. So he can send zeros to one guys and one to another guys, and then they will not see a consistent view on the value that has been broadcast. Good. So in particular, so our corruption model, we assume a static adversary who can corrupt up to T players. So you can think of it as a virus. Virus kind of enters the system, chooses T guys to corrupt, and now they behave maliciously. And you still want to simulate broadcast in such a setting. Okay, so now we have this task to implement broadcast, and the first result was from the 80s. So it has been shown that if the number of corruptions, number of guys who are controlled by this virus, are at most 1/3 of the total number of parties, then you can implement broadcast, okay, even with perfect security. So later, this result has been extended by Dolev and Strong, who showed that if you can assume signatures, meaning that in the beginning there is something like public key infrastructure which is distributed in the system, then you can implement broadcast tolerating any number of corruptions with cryptographic security, given that your signature scheme is good. And later, actually, Fitzman and Weiner in '96, they showed that in this particular setting, because you already know the set of predefined verifiers, only the guys in the system should be able to verify the signatures, you can consider kind of a new object which is called unconditionally secure signatures. So we do not assume any cryptographic assumptions, and they still allow you to implement broadcast. But they're kind of limited in a way that you can only send your message that can be verified only by a limited number of verifiers. So if in this setting you have one public key and one that should be used for verification, here are many public keys for verification. Okay, so these are the feasibility results, and now let's talk about efficiency. Okay, so now we know that we can implement broadcast. The question is how efficient it is. So let's say we want to broadcast L bits. So the sender, he wants to broadcast L bits efficiently. So the trivial lower bound that we can guess in this case, the number of bits that should be communicated is at least the length of a message multiplied by the number of players. Why? Because everyone should at least learn the value that being broadcast. Okay, so now this is kind of the goal. We want to be able to match it. And indeed you can do it. So for the settings, the number of corruptions is not too big. You can do it for the threshold and third. And later it has been shown, not later actually, before, but it has been also shown that you can do it, the number of corruptions is at most in half. And what we show today in this work is that you can actually do it, you can achieve optimal communication complexity even if number of corruptions is arbitrarily, okay? So in general, kind of the flow of a work in distributed computing in this setting, in Byzantine environment, is that you start with implementing the protocol, check if it's feasible, and then you kind of try to tolerate as much corruptions as possible. So here kind of is the ultimate case. We can tolerate any number of corruptions. So this is very nice. Okay, so let's give a small overview of our protocol. So remember, we want to broadcast now a very long message, okay, of L bits. We'll start our protocol by taking the message and dividing it into Q blocks. So we will split it into many blocks. Okay, so and then we will introduce something that's called optimistic block broadcast. In some cases, the block can be implemented very efficiently with optimal cost, and in that case, this protocol will give us some overhead. So it's kind of, in some cases we are good, in some cases we are bad. And then we will just take our message and broadcast it block by block, such that number of bad cases are limited. And then finally, we can compute this overhead from the bad cases and choose the number of blocks, such that asymptotically this bad overhead will vanish. So this is kind of the general structure of our protocol. So this protocol, so it will come with the next slide exactly. So we want to tolerate any number of corruptions, and we also assume that there is something like a setup. But when we describe our protocol, we will actually assume that there is some other broadcast protocol which may be inefficient. So essentially, we don't really say what exactly setup we need. We just say that there is a way to broadcast few bits, even inefficiently, but we are okay to use it. So when you take the previous protocols from the feasible world, and we can use it here. Okay? So now I'll describe you the optimistic way to broadcast one block. So the design requirements for broadcasting one block are the following, is that in some good case, we have optimal communication costs, and in some cases, we get some overhead. Okay, so now here is our assumption. So we start with the sender. He has some block that he wants to broadcast. He will broadcast the digest using some collision-resistant hash function of this block. And when I'm saying here broadcast, this is kind of answers your questions. Your question is that it's kind of, we try to implement broadcast using another broadcast. It's a little bit strange, but here it's okay because we will use this broadcast only to broadcast few bits. So we're not going to broadcast the whole block because it will be just stupid. Okay, so we're going to broadcast only a few bits, and these few bits are this digest. Okay, and this we can do using some inefficient protocol. So using any broadcast protocol. So we kind of, this will come later. So we can use some inefficient protocol to do this, and we will see that in asymptotical, it will not matter. Okay. Yes, so we'll take one of the feasible protocols, by Dolef-Strong, or Fissman and Widener, anything. And our protocol will just use it as a black box. Okay, so we start by broadcasting the digest. So now we have a collision-resistant, we kind of, our assumption is that we have some collision-resistant hash function. Okay, and then we just start by iteratively propagating the block that we want to broadcast. So essentially, once we have a digest, we can separate all the players in the game, in the green players, the one who know the message, and then the white players who still don't know the message. Because once you know the hash, you can efficiently say if it's a good message or not. And it's kind of, in a way, broadcasting this hash, it kind of commits the sender to this message. So there can be only one message in a game. And everyone wants to learn it. So what we do, we have this green set of the guys who know the message, and the white set of the guys who don't know the message. And we're going to propagate the message via the links, via the communication links. Okay, so this is kind of a public knowledge. Okay, the green set and the white set is a public knowledge. So we choose an edge between the white set and the green set and try to propagate a message. So what can happen is that, for example, this guy receives a message and he sees that it has the right hash. And then he broadcasts 1 bit. So remember, we have this assumption that we can broadcast few bits. So now we will use this assumption again. We can say you can broadcast 1 bit. Given that the message is long, it will not matter. So he will broadcast 1 bit saying, look, I'm happy, I want to be in the green set. So we put him in the green set and we repeat the procedure. Okay, we choose another guy and he can also become green. But now what can also happen is that a new guy receives a message, checks the hash, and he is unhappy. So he broadcasts a bit saying, look, I received the wrong message. So now this can mean 2 things. Okay, this can mean several things. In particular, this means that these guys, they kind of hate each other. Because the green guy is supposed to know the message, sends it to the white guy, and the white guy checks the hash and says it's a wrong hash. So more or less, the white guy accuses the green guy. Okay? So now, this means that either white guy is malicious, or the green guy is malicious because he sent the wrong message, or both of them are malicious. So essentially, once we have this knowledge, we can exclude all communication between these 2 guys. So we mark this link as a bad guy, as a bad link. Okay, finally, we choose another edge. Again, the similar stuff can happen. And finally, we can complete the propagation of the message that the white guy finally becomes green. Everyone is green. So as you can see here, some iterations are good. Kind of, we use the propagation of a block in order to make someone green. And some iterations are bad. Actually, we paid in this conflict finding. Okay? So the total number of iterations, let's say it's n good iterations and let's say di bad iterations. Then we can compute the total communication cost of this protocol. So you need to broadcast the hash. And 1 iteration costs you just propagation of a block and broadcasting 1 happy bit. So this BC1 is that we use the black box broadcast in order to broadcast this number of bits. So the total cost is broadcasting the digest plus the number of iterations multiplied by the cost of 1 iteration. Very simple. Okay, so now we can compute the total cost of our protocol. So this is our long message. We split it into q blocks. And one propagation of 1 block, it costs us this. Okay. Now we will use this our assumption that the message is very long, and I will tell you later how long it is. And we can actually say that broadcasting few bits doesn't matter. So essentially, it's the number of iterations multiplied by the length of a block. Okay. So now we can do the analysis of the whole protocol. We can just compute the sum over all blocks. So we take this expression and sum over all blocks, and we see what happens. So we see that the number of conflicting edges, they appear here as a sum. So now we use this our assumption that our adversary is a static one and has to corrupt everyone and cannot change the corruptions. So we know that the total number of bad edges that we have is at most n squared. So we will never reuse bad edges because once we know that there is a conflict between 2 guys, it kind of stays there. It doesn't make sense to communicate over this edge again. So given that we know that this is bounded by n squared, we get this bound on the communication complexity. And now it's trivially, of course, if you choose a number of blocks to be n, you get optimal communication complexity. Good. Let's review the protocol. It's very simple. We take very long message, split it into blocks, and we introduce something which is called optimistic block broadcast, and optimistically broadcast our message block by block. Finally, we notice that if we choose the number of blocks to be good, then our total communication complexity is also good. Very simple. Okay, so good. Now we know that it's feasible. We can achieve optimal communication complexity for any number of corruptions. This is good. And kind of the drawback, one of the drawbacks is that we have only cryptographic security. So we need some collision-resistant hash function in order for this protocol to work. So now a simple question, can we do better? Yes, we can actually get rid of a collision-resistant hash function. So now I will show you how to get rid of it. Okay, so this is kind of a standard approach. If your protocol uses, or any scheme uses some hash function. A standard way to get rid of cryptographic assumptions about it is to use universal hashing. Okay, so what is a universal hashing? So traditional hashing, you have a set of messages, like a SHA function, and it just maps messages to the digest, to the set of hashes. You have one function and you use it, it's good. Okay, and universal hashing is a family of functions. Let's say there is some family, h1 up to ht. And each of the functions of the family, it maps messages to the digest. Okay? And the security of this families is following. If you fix two messages, we can fix the messages. And we can just go to each of the function and check if there is a collision for this function. We can take h1, check if there is collision, take h2, check if there is collision, and so on. We know that for any fixed two messages, the fraction of colliding functions is at most epsilon. So we know if a function is chosen at random, then it's most likely to be a good function. Okay. So just to compare it with the traditional hashing, of course, if you fix hash, if you fix a function from a family, then it's easy to find collisions. So you cannot fix a guy from a universal hashing family and use it. Okay. So just a fact. So I will not describe it in this work, in this presentation, but we know how to construct good universal hashing families. So we know that so we know that given the domain size, we can choose the size of a hashing family and the size of a digest space to be small enough. Okay, good. So this is universal hashing, and now what we're going to do with our protocol. So this was before. With cryptographic hash, we do the following. We broadcasted the digest of our block, and then we propagated it step by step. We take an edge, propagate it, take an edge, propagate it, and so on, and we have this invariant that the green guys, the set of green guys who know the message, it always grows because the message becomes fixed. And they always have the same value. So we want to preserve something like this, but now we don't have a cryptographic hash, so we cannot broadcast this hash from the beginning. But we want to do something similar. So with universal hash, we do the following. Now I will describe you one iteration. Okay? So one iteration will work as following. So as before, you have a set of players. Some of them are green and some of them are white. And what we're going to do, we choose an edge between the green set and the white set. So we want to propagate our message. So now the new guy doesn't have an easy way to verify if the message he receives is good or not. So what he's going to do, so now the green guy sends the message, sends his block to the new guy, to the white guy. And then the new guy, he can actually, it's his responsibility to ensure that he has the right message. So he will choose a key for the universal hashing family at random. So this is the place where we use the universal hashing. So now he chooses the key at random, and he broadcasts the digest that he has. Says, look, for this random key, I have this digest. And now all other guys can do the same. They now know the key, some key is chosen, and they will broadcast the digest for this key. So there are two cases that can happen. So let's say in the positive case, in the good case, everyone broadcasts the same digest. So if everyone broadcasts the same digest, then given that if P3 is good, then the high probability has the same value as all the good guys. So in this case, we can safely add P3 to the green set. So this this is a good case as before. So we grow the green set. But now in the bad case, there are some different digests. We have to do some more work. So we have to do something that we call extracting a conflict and then restarting the algorithm. So extracting it means that we'll still find the conflicting edge, but not necessarily this one anymore. So this red edge which we took, it will not necessarily become dotted. This is one thing, and the second thing, we're going to restart the algorithm. We're going to set the green set to be only the sender again. So before here, we didn't need to restart, so the green set always grew. Now, green set can shrink, but will grow again later. Okay. So now how the extraction of the conflict works. So this is the green set, and this is the new white guy, the candidate, the one who wants to learn the message. So first of all, observation number one, in the green set, actually, green set has some structure. It's not just random guys. They actually form something like a learning tree. So it must be the case that I learned value from someone. It cannot be the case that I learned value from nowhere. So there can be, for example, a cycle. Okay? So, and the sender is in its root. So you can choose, actually, you can check who learned value from whom. Okay? And this is the candidate, and he is now at this age. This is one observation. The second thing is now we know that the candidate will broadcast his random key and the hash. Now let's mark him with plus by the guy who agrees with his hash. Now we can observe that some of the guys here have pluses and some minuses. Okay, so plus if I have the same hash with this guy or different. Okay, and we know that because we want to extract a conflict, not all the hashes are the same. So it must be the case that there are at least some guys who have pluses and at least some guys who have minuses. So now we have a tree marked with pluses and minuses. There must be a plus minus h. Okay, so let's say this one. And what does it mean to have a plus minus h? This guy learned value from this guy. It must be the case that they have the same value, but they produce different digests. So it must be the case that one of them is at least lying. Okay, so now we identified again the two players and one of them is bad. And this will be the conflict. Now essentially what is bad, we forget about this tree. We could have saved some guys in the green set, but we do it very pessimistically. We say, okay, forget about all the guys in the green set. We will cut them all and leave only the sender. Okay. So just I will give you an example how it works then. So you again have a set of guys, a green and a white set, and you propagate the message. You successfully propagate, but now when you have a conflict, you will extract it and then you do restart. So this means that the green set shrinks to the sender again, and now there is a new edge, which is not necessarily the one that you considered in the last step. So this is the difference. Okay, so when you again can propagate, propagate, and propagate, you propagate, and again there can be a conflicting situation, a bad case, and then you again extract the conflict and you again do a restart. Okay, you do it again, and then finally you are done. So everyone becomes green and you're happy. Okay. So finally, let's say you have at least, so say we have a DI restart. So in this case, we have two restarts. And the cost of one iteration is just to send the block, and then you need to do some broadcasting. And we also assume that, so here I said broadcast of kappa. So kappa is the size of the hash and the random key. Okay. So we also assume that the block is long enough, and this is kind of small. This is already a stronger assumption, but still we can do it. So the total cost will be the number of iterations plus this is the cost of one iteration. And then as you can see here, DI is again appears, and we're going to do the same trick as before. We're going to take the message, we cut it into blocks, and then we re-estimate the size of one iteration. So essentially it's this number of this propagation steps multiplied by the length of a block. We again take the sum, and you can see that DI again can be nicely separated. And again we say, okay, number of conflicts is at most n squared, and then we can bound everything by this expression. So now, again, we just see that if you choose Q to be n squared in this case, it's enough to achieve optimal communication complexity. So this is a relatively simple idea, but apparently the previous algorithms, they did something else. So I think this is kind of the simplest protocol you can give in this case. Okay. So just now I will kind of show you where we cheated in a way. So let's go to cryptographic case. So the only known protocol by Dolph Strong from '83 has this communication complexity. So it's quadratic ln squared. It's a dominant term. So ours becomes ln, but here we pay additionally n to the power of 5 kappa, where kappa is a security parameter. So if you talk to anyone who does some practical work, n to the 5 is already very bad. So our protocol is optimal, but asymptotically. So of course, if your message becomes at least n to the power of 5, then you can say our protocol is good. But for shorter messages, we are not better. So this is like the length of the signature. So our reduction, it uses this protocol to broadcast few bits. So it's okay, it's the length of the signature and the length of the hash. So we assume that the hash is collision resistant, so we get some error from there, and the fact that this protocol will work from the signatures. So kappa is the length of the signature and the hash. Okay. So it's not so practical. In the information theoretical case, it's even worse. So we get n to the power of 10 kappa, the kind of this additive constant. So okay, asymptotically we are good, but the concrete parameters are quite scary. Okay. So in the remaining part, I will talk about something else, the round complexity. So given like this table, you already say that the protocol is not very good because it has these additive constants, which makes it quite impractical. But actually, there is another issue that makes it also impractical. But we need to talk about it. So so we achieve optimal communication complexity asymptotically, but we also need a lot of rounds. So our both constructions, we take n squared and then n cubed rounds. This is a lot. So, but actually what we can show that we need at least n minus 1 rounds. So we show that we cannot beat the linear number of rounds anyway. So it's not exactly, we cannot match our round complexity, but it at least shows that you cannot hope to get like a constant round protocol. So this is not possible. So, and just, before going to this impossibility results, I will briefly tell you about how, in general, impossibility proofs they work in distributed computing. So what I've shown before was like the positive result. So it's easy to give a protocol and prove that it works. Okay, it's relatively easy. But proving impossibility results, the impossibility statement, it turns out to be much more complicated. So essentially, if you check the literature and see impossibility proofs, they all kind of follow a similar pattern. So they all go by contradiction. You assume that there is some protocol pi that solves the problem. So it doesn't matter if it's about broadcast or anything else. Then you assume that there is some protocol pi that solves the problem. Then you kind of draw a very cool picture composed of the programs. So you say that there is a protocol. It gives protocol pi y to the player p1, pi 2 to player p2, and so on, pi n to player pn. Then you connect this program smartly, and then you derive some contradiction. So essentially, if you have this picture, you are good, because then you can find some contradiction in such a picture. If you don't know how to draw this picture, or you have tried all the pictures, then you don't really know what to do. So just as an example, I will give you the classical proof. Before showing our impossibility proof, I will show you how the classical impossibility proof works. So this is the first statement that there is no broadcast protocol among 3 players and 1 corruption. So I'm naming here several kind of works, because in the first paper where this was shown, it hasn't been shown like with this statement. So it has been shown that there is no broadcast protocol. But now we also want a stronger statement. Every broadcast protocol will fail with at least this probability. So this makes it stronger. Okay. So as I said, we need to draw a picture. So we assume that there exists a broadcast protocol for 3 players that tolerates 1 corruption. We draw this picture, and we give input 0 to the left copy of a program pi1, and give 1 to the right copy of a program pi1. Okay? So now, this is just a random system. So we assume that there are programs, we can connect them, and we can just execute this random system. Okay? And as a result of this execution, let's say this program pi2 produces a value v2, and program pi3 produces value v3. So now we can say that broadcast, so by analyzing the properties of a broadcast, we can do the following. So we can look at this part as the one that can be simulated by the adversary, program pi2 being executed by the player p2, and program pi1 being executed by the player p1. This gives us the requirement that v2 should be 0. Okay? Similarly, if we let adversary to corrupt p2 and execute this random part of the system, and player p3 execute pi3, and player pi1 execute player p1 execute this pi1, we conclude that v3 equals 1. Finally, if we take adversary to corrupt player p1 and let player p2 and p3 execute these 2 programs, we conclude that v2 should equal to v3. Okay? So finally, our statement is proven as following. So what adversary does, he chooses, okay, and as you can see here, these are the requirements. So of course, no matter how you choose v2, v3, or v2 or v3, these are random variables, one of these conditions is violated. Okay? So now the program of adversary that will fail the broadcast protocol of probability at least 1/3 can be described as following. So adversary chooses one of these pictures. He can choose either to be this guy, or to be this guy, ought to be this guy with probability 1/3. And this will be the adversary that will break the protocol with probability 1/3. Why? Because he will guess the right edge. Good. So, okay. So now we know this framework. This is an example how it works. And now we're going to apply it in order to show that every broadcast protocol that tolerates any number of corruptions and that takes less than n-1 rounds will fail with probability at least 1/2n. Okay? So just the way it's written here, so far it's known. It's based on the work by Garay, Katsku, and Ostrovsky from 2007. I will show later how we modified it. Okay? So again, we draw a picture. This is what we start with. We draw a picture. There's a player pi1, there's a program pi1, pi2, pi3, and so on. They're connected in such a chain. Okay? And we let pi1 to, its input will be now not a fixed input, it will be a random variable v. Okay? So this will be a random variable v. And just note that normally every program has a lot of interfaces. It communicates with many different guys. And now all the interfaces will be cut. So they are not drawn. It means that there is no communication. So this program pi1, it doesn't communicate with program pi3. So there is like a null device. There is nothing coming from it. So now we draw this picture and we can do again the analysis. So okay, this is a random system. There are some outputs. So in broadcast, again, we can check what are the requirements of a broadcast. So in this case, we can see that it can be the case that the adversary corrupts all these players, and these two guys are good. It means that v2 should equal to v. So this is a validity property. Okay. Similarly, we can take every two guys in the middle of a chain, and they should agree on the same value. So it means that vi equals to vi plus 1. And finally, let's take the last guy. So the last guy, actually, because we assumed that we have at most n-1 rounds, smaller, strictly less than n-1 rounds, there is no way he can learn any information from the sender. So it cannot just propagate to him. So the mutual information between this output value vn and v is 0. Okay? So basically, this means that, again, as before, there is an adversary that can choose any of these sets and can corrupt one of them with a uniform probability, and there will be a problem with probability at least 1/2. So there is a chance that this guy can guess the correct value, but the probability at most 1/2 multiplied by 1/n, our uniform choice, we can make the protocol fail. Yes? So you have, okay, so we assume that there is a broadcast protocol that can work for any number of corruptions, and it works in smaller than n-1 rounds. Okay? So now we connect the programs as described in this picture. No, it doesn't assume that, it's just a picture that we use. Okay? And so this program pi1 is connected to program pi2. It's supposed also to talk to program pi-n, but we cut this interface. Okay, so now we know that the communication happens in steps. Okay, so in step number 1, pi1 can send something to pi2. In step number 2, now this information can be sent to pi3. So this is how information is propagated. Of course, in the first step, also pi4 can send some random stuff to these guys. So it's just a random system, and this is just the random variables. So we can define them and now analyze the properties of these random variables. Okay. So the final statement is that the last guy, because we do this n-1 steps, and because we have this chain, and we could cut really this communication, the mutual information between the output of the last guy and v is 0. Okay? And then again, the strategy of the adversary is to corrupt one of these, to use one of these gray areas to be corrupted and execute exactly these programs as it's in the picture. Okay. So now what we noticed is that assume now that we even give Oracle access to a smaller broadcast, the stuff that we have been doing in our protocol. Even we let the guys to broadcast few bits. So I can say if I'm happy or I'm not happy. I can broadcast a hash additionally. In this case, the whole argument will be repeated with the differences that the mutual information will be smaller than the entropy. So this, all the mutual information that you can get is at most the information that is broadcast via the oracle. And as long as this information broadcast via the oracle is kind of non-trivial, you don't abuse the oracle to broadcast the whole message, then still it will be smaller than the entropy. And at least with this probability, the last guy cannot guess the right value, and then it means that there is a problematic edge. And now the adversary who chooses an edge at random can still win the game. Okay. So this is the impossibility proof. So it shows us that even if we wanted to improve the round complexity of our protocol, we still cannot go better than the linear number of rounds. So our protocols, we take n squared and n cube. It's not clear if you can close this gap. Okay. So now let's go to conclusions. Yes. Sorry? How many corrupted parties are? The corrupted parties, okay, so now it's a side remark. So actually we know that you can get constant round protocols, expected constant round protocols, if t is smaller than n half. So it seems that you can, so for example, this shows that from t smaller than half you can go to t smaller than n and preserve optimal communication complexity, but round complexity you cannot. So it's very inefficient. Okay, so let's yes. For n over 2, so, okay. So here we can assume that every two guys can be good and everyone else is bad. So if you have n over 2, then you immediately get only this kind of pieces. So you get, you cannot abuse it in the same way. Okay. So now let's conclude. So, okay, so what we did today, we presented this first protocol that achieves optimal communication complexity for broadcast, okay, and tolerates any number of corruptions. So future research will be okay. As I said, that we're not so happy with these additive constants, so we don't know what to do with them. We don't know how to prove lower bounds, because I don't know how to draw a picture. If we don't know how to draw a picture, we don't really know how to prove lower bounds. Okay, this is one limitation, and another one is that our adversarial model assumes that we have a static adversary. So I think that we can extend this to adaptive adversary, but for example, a mobile adversary we cannot. Because this is the whole idea of mobile adversary, he can corrupt someone and then stop being corrupted. And our analysis assumes that once someone is corrupted, he always stays corrupted. So we don't know how to extend these results to this case. And the second part is that, and this is kind of the stuff that you can do inside the broadcast problem. You don't care about anything else, just improve the current state and do something. So what you can also do, you can say, okay, we know that broadcast is very inefficient, and let's try to do something else. So one of the ways out is to consider weaker versions of broadcast. So there is something called weak broadcast, graded broadcast, two-threshold broadcast, and so on. It's kind of a weaker variance of it, and there is a hope that you can implement some of them more efficiently. This is one thing. Second thing is that you can say, okay, I have a protocol and I'm using broadcast. So I know that broadcast is very expensive anyway, so I'm going to try to save as much as possible. So I'm going to use the broadcast as few number times as possible. And this is kind of, for example, you can do verifiable secret sharing and using broadcast as few times as possible. Okay, and finally you can just say, okay, I give up, I take my multi-party computation protocol and I just analyze what happens if I get rid of a broadcast. So can I get some fairness, can I get something, and you can also do this.